Hello, welcome to my Module 3 presentation. Just opening it up. Okay. Hello, welcome to my Module 3 presentation. Today I will be exploring the general linear model, specifically the two sides of the general linear model, which are regression and ANOVA. Now, the general linear model itself is a very statistical tool and it allows us to create many different models to describe the world in which we live. And this can be represented by this equation. Our data equals our model, so what we describe, plus any error. So the error is what our model doesn't describe. This is interesting to kind of understand. But specifically, I'll be looking at regression and ANOVA as a means to help explain what we see in the world. So specifically, I will be a consultant for Netflix, and I will be trying to predict Netflix viewership. So for MRC, I will be looking at what predicts Netflix viewership using three independent variables of homework amount, day of the week, and anxiety levels. And if those can predict Netflix viewership for individuals. Then for ANOVA, I'll be looking at what genre of TV show / movie provides the most viewership. So my two groups for that are comedy and drama, and I'm interested to see if there's a difference between those groups and how they predict Netflix viewership. So to begin, before we start, we can just go over some similarities and differences between MRC and ANOVA. So just to begin, they're both part of this general linear model, which means they carry similar assumptions, hypothesis testing, and they're linear and additive. And overall, they help us understand some variance in the world. However, they do possess a lot of differences as well. So first, at their base, regression uses correlation because it's interested in relationships and predicting relationships, while ANOVA at its base is a t-test because it's interested in differences between groups and how that can lead to predictions. They also have different names for errors. In regression, errors are called residuals, and in ANOVA, they are called errors. And in regression, variance is attributed to the individual, while in ANOVA, variance is attributed to groups. But the main difference between regression and ANOVA comes down to flexibility. So regression is very flexible. It's a very flexible tool, and we can look at our residuals to understand how to change our model to help better predict what we want to predict. Versus ANOVA is very strict and it's very inflexible and believes the model is always right. So if the data doesn't fit into the model, then that just means that's not the data we want to use. So overall, regression can do all ANOVA can do and more, while ANOVA is kind of stuck with what it can do and then just doesn't try to understand what it can do. But first, we'll look at regression. So regression can be signified by this equation, and its parts being y is our dependent variable, the b naught is our intercept, the x is our predictor, the b is the weight of our predictor, and the e represents its residuals. So the overall purpose for MRC is to help us explain relationships that we see in the world, and we can add more predictors to help understand this prediction that we hope to understand. But with regression, it comes certain assumptions, specifically 9 assumptions that we should look at when consulting outputs in our model. Now with regression, we don't have to always follow all of these assumptions at the same time because some of them are just unrealistic, like there being no measurement error. We're dealing with humans, we're dealing with people, there's always going to be some sort of measurement error to take into account. But it's always important to check these assumptions against our model to make sure we can understand what our model's saying. So when we look at our model, we'll go back and check a few of these assumptions just to make sure we're not violating any. And like I said, with our MRC model, we are going to be using 3 independent variables to predict our dependent variable, which will be Netflix viewership. So first, you can see the normality of our dependent variable. It looks pretty normal. Again, we have a small sample size, so if we had more participants, this would probably look a little more normal, but it's nothing to worry about. But before we look at our output of our linear model to see how our independent variables predict our dependent variable, we should first plot the data to make sure we know what we're looking at so we can't be fooled by our output. So here we can look at 4 of these assumption plots here, the first being our residual versus fitted plot that we can use to test our assumption of there being a linear relationship. And this overall checks out. There's no patterns that we see here. They all follow around at this horizontal line. So that checks out for linear relationship. Then we have our normal QQ plot, which is used to assess if our residuals are normally distributed. Which would mean they follow along these lines, which they for the most part do. There are a few that don't, like 0.14 and 0.20 and 26, but we can just keep that in mind, but it's nothing too concerning. Then below here we have our scale location plot, which allows us to check the homogeneity of variance of our residuals. So basically, this checks our homoscedasticity, which homoscedasticity just means that we have equal variance of our residuals and they have the similar scatter. Now, if they had a different scatter, which would mean they open up in a cone-like shape or something like that, that means those are heteroscedastic, and that is not what we want. But here it looks like we have homoscedasticity, which is great. And then our final plot here is our residual versus leverage plot. And this plot is very important to determining if there are any observations that may create differences in our results. So we can already off the bat see that 26, 28, and 14 might be creating some issues, but we'll look more into this later, but it's nothing that we can't already run our model for. It's just something to keep in mind. So we ran our model, and as you can see here, we have our estimate, which is our signal, our slope, the b-value. And as Kristina says, this tells us how much our dependent variable is expected to increase when our independent variable increases by 1, but all the other independent variables remain constant. Then we have our standard error, which is our noise and allows us to value our uncertainty to see how our sample fits in our population. And then we have our t-value, which is associated with the degrees of freedom and gives us our p-value. And then we have our p-value, which from null hypothesis significance testing, we know that we want it to be below 0.05 so that we can reject our null hypothesis. But the interesting relationship to note before we go into our p-value is the relationship between standard error, t-value, and p-value. So as standard error goes up, our t-value goes down, and our p-value goes up. And this is because the more uncertainty in our model that we have means we can't fit under the limbo bar of our p-value. So the more uncertainty we have, the less that our model can predict what we want. So then that leads me into our R-squared, which is our coefficient of determination. So this is supposed to tell us how well our linear regression model fits into our data. However, we don't want to completely rely on this, as King says, because there is no statistical tool behind this. There's no theory behind it. If we're interested to see how our linear model is actually predicting what we want it to predict, we should look at standard error, because that's actually all this coefficient of determination is trying to tell us, and standard error has the theory to back it up. So now we can look at our p-values. Our null hypothesis in this is that there's no relationship between homework amount, day of the week, anxiety levels, and Netflix viewership. And as you can see here, all of our p-values are above 0.05, meaning we failed to reject our null hypothesis. So this is kind of interesting to me, so we can look at our assumptions more to kind of understand what's going on with our independent variables and see if there's anything we should look into more. So first, we can look at our homoscedasticity. So I plotted each independent variable against the residuals to see if they have equal variance. And as you can see, they look pretty equal, so that's probably not a concern we need to think of. Then we can look at this residual versus leverage plot again. And like I said before, there are some outliers here, but as Kristina says, we don't just want to throw out outliers to throw out outliers. We need some guidelines to make sure we're not throwing out important data points that can alter what our model is looking like. But we didn't create any of those guidelines, so we'd want to do that in the future. Data point 14 here, though, is really interesting, and it's a pretty big red flag because it appears to have a high Cook's distance. And having a high Cook's distance determines its influence on our model. So if it has a high influence, that means its inclusion or exclusion can alter the results of our model. So maybe its inclusion is making our model not reach significance, but maybe its exclusion would actually do the same thing. So there's more to explore there that we should look at, but it is a red flag to take note of. Then finally, we have multicollinearity. Now, multicollinearity just means if we have any independent variables that correlate more with each other than they do our dependent variable. So as you can see here, that is the case. Homework and anxiety correlate more with each other than they do Netflix time, which is alarming. And day actually correlates more with homework than Netflix time. So to look at that further, we can look at our VIF value, which is our variance inflation value. And this tells us that homework and anxieties don't necessarily have high VIFs because that's not really what we look at this for, but they are close to 2, which means they're increasing our standard error by about that much as well. And as we know, as our standard errors are inflated or they increase, that decreases the probability that we can reject the null because that sends the p-value up as well. So that's something to be concerned of and we should look more into. So I was interested, so I ran a bivariate regression to kind of see how our independent variables related to our dependent variables and if the introductions of new variables, independent variables or predictions or predictors were changing that, which they were. As you can see, homework and anxiety, X1 and X3, when they're by themselves predicting our dependent variable, they actually reject the null hypothesis of there being no relationship. But when they're together, they do not. So that's telling me maybe they're influencing each other in some way. But then we have day, X2, and it's showing me that it's not a very good predictor of our dependent variable. So maybe we shouldn't have included it at all. The next thing we can look at are types of sums of squares. So since I was worried about multicollinearity, maybe we should also consider the role that shared variance can play in our results. So our types of sums of squares just mean that it's the sum of our square of variation. So there are three types that we can consider. So type 2, which is the standard output of R, is differences of kind. So it's ordered hierarchy. So main effects go first, then interactions, then third order effects, and so on and so on and so on. And that is what our other model was when we failed to reach significance in our prediction. Then we have type 1 sums of square, which is sequential hierarchy. And this basically tells us that the order that we put our independent variables in matter. So what's put first is they get all of their part of the pie. They get all they want to eat, and then the next independent variable comes and they get all, but they don't get anything they share, and so on and so on. So I ran those, and you can see that order does seem to matter, and that if homework comes before anxiety, homework's p-value is a lot lower than anxiety. So this is telling me homework and anxiety probably share some variance with each other, which is something we should really consider because we want our variables to have their own unique variance. So we should look into this more because it's a little concerning. So what is this telling me? So this is telling me we should look more into multicollinearity. Specifically, we should look into errors of commission, making sure homework and anxiety aren't just measuring the same thing, because that can be throwing off our model. And then we should also look at errors of omission. Maybe we should have included something other than day because day doesn't seem to be a good predictor of Netflix viewership. We should also look at our outliers. We should look into our data and see what data point 14 is really telling us, looking at its hat values more. But overall, we should check our model. So it doesn't mean that there can't be predictors for Netflix viewership, but maybe we just didn't include the right ones. And because it's regression, we can change our model around a bit. So now we can move into ANOVA. And ANOVA allows us to compare groups. It allows us to see the differences in groups and in what groups those differences lie, although it doesn't tell us where our individual differences are, which is another thing that we could improve on ANOVA, but it does tell us if there are differences. So ANOVA follows a certain set of assumptions. It does follow some assumptions over from regression because they share the general linear model, but it does have its own assumptions as well, which are called IID, which are independent errors, identically distributed errors, and normal distribution of errors. And in ANOVA, since it's very inflexible, you cannot violate any of these assumptions. If you do, then your model's no good. You need to throw it out and start over. So this is our output. And as you can see, again, we failed to reach significance in our data. That means we failed to reject our null hypothesis of there being no difference between groups. And so we need to look into the assumptions and make sure we didn't violate any of our assumptions since our p-values are all above 0.05. So here we can use these analyses to check our assumptions. Specifically, we can use our Levine's test here to check our assumption of making sure our errors are identically distributed. And as you can see here, we have a homogeneity of variance. That means that our variances are the same because our p-value is above 0.05, which is what we want to see. We do want to fail to reject the null hypothesis in this case. Then in Shapiro's test, we test the normality of our errors. And again, we want our p-value to be above 0.05 because we want to fail to reject our null hypothesis of there being no normality. So this checks out as well. Then we can look at our degrees of freedom, which tell us if we have independent errors. And our degrees of freedom match up to what they should be, so we don't have any nested data or anything like that to worry about. Then we can look at our normal QQ plot. And our normal QQ plot tells us the distribution of our errors. And they look fairly normal as well, so we're not violating that assumption. And lastly, the last thing we can look at to try to understand why maybe we failed to reach significance is our design, to see if our design is balanced. And a balanced design means we have equal sample sizes in each group. So we had 30 participants in the comedy group and 30 in the drama group. So we did have a balanced design. So to me, it seems like we didn't violate any assumptions glaringly, at least with ANOVA, so that's not what's going on. So it's telling me that there's probably no differences between groups, but this could be a result of a type 2 error. And again, type 2 errors are when we fail to reject the null hypothesis when we actually should. So maybe there is a difference between group where we just didn't measure correctly. We didn't use correct measurements. And this could be that we didn't differentiate between groups well enough. We grouped TV shows and movies together for comedy and drama, so that might be becoming some issues. So we should look further into that. But overall, we need to follow the advice of Kristina, in that numbers are only part of the story. So in future research, we need to seek to understand what our models are trying to tell us and what our numbers are telling us. Because although we fail to reach significance, this could be a result of, one, for regression, we need to create a better model. We need to make sure our variables are what we want them to be, and we're modeling what we want. And then with ANOVA, we want to make sure we're comparing the appropriate groups to actually understand the differences we seek to understand. But thank you.